Okay, so we had seen the different types of capacitances that are associated with CMOS inverter. Okay, and so what we do is here, so we will replace, we will make it more simple in the sense that all these capacitances are there. So we will try to connect, we will try to take into account all these capacitances, and we will replace this with the single capacitance called as C load. Okay, this is present here at the output terminal. Look at this C load. Okay, and what it is the combination of CGDN, CGDP, CDBN, CDBP. Okay, and the interconnect capacitance and the gate capacitance. Okay, so from N MOSFET we have taken two capacitances, okay, CGD between the gate and the drain, and CDB, so basically GD and GD, so this part, and DB, drain and body. Okay, GD, gate and drain, and DB between drain and body. Okay, and from P MOSFET it's been taken again CGDB, CGDBP, so gate and drain, so this capacitance was taken, is taken, and CDBP, so drain and body is taken here. Okay, CGD between gate and drain, and CDB between drain and body, okay, right, so this is taken here, and uh, and yeah, this one also the internet capacitance. So basically, so this capacitance, so CGDN, okay, CGDN, this is taken, CGDP, CGDP, this one is taken, CDBN, this one is taken, and CDBP, and D, drain and body, this one is taken, right? Okay, right, and the interconnect and the gate capacitance. So basically these four capacitances are taken here. Okay, so okay, this one, not this one actually. Okay, right, and also the interconnect capacitance and the gate capacitance, right? And why not to take this one, CGSP and CGSN, is that since this is connected to the input side, so it will not be taken, and like this is connected between input and the ground here, and this is also connected, CGSP is connected between input and the supply voltage. So it is basically connected at the input side, which is not cannot say that it is directly affecting the output voltage. Okay, but if we for the next stage definitely these two capacitances should be taken into account. Okay, for the next stage these input capacitances will become the input capacitance from the next stage. Okay, and will come here in this part CG. Okay, and this is also coming at the output side of the first stage and input side from the next stage. So we are not ignoring this CGSP and CGSN, just we are saying that since these are present at the input sides, okay, so let us take this CGSP and CGSN at the input terminal of the next stage, okay, which will come and get reflected inside this CG. Okay, and look at this, the CSBP and CSBN here. Look at that we know that C is equal to Q into V. So if voltage is 0, this C becomes 0, right? So what is difference? And look at, if we know that for this CSBP, the source and body are connected at the same terminal, and hence the voltage difference between this is 0. And similarly for this N MOSFET also, this source and this body, the voltage difference is again 0. So in effect, the CSB and CSBN will be equal to 0, and will not be having an impact on the analysis of our circuit. Okay, so what we can do is we can draw an equivalent circuit. We can draw an equivalent circuit. Like this, okay, where we have this P MOSFET and we have this N MOS, okay, and we have just one single capacitance connected at the output terminal, and this is called as C load, or the load capacitance. And basically this C load will be the combination of all those capacitances that we had seen in the previous picture, in the previous diagram. So there is a single capacitance present here at the output terminal, which is a kind of lunt capacitance, and which is the summation of all those capacitances that we had seen, that we had shown individually in the previous diagram. Okay, so this is the simplistic view. Okay, we have one PMOS device, one NMOS device, so we have one CMOS inverter circuit. Okay, CMOS inverter circuit, and this is the input signal, input voltage. This is the output terminal, output voltage being taken here, and we have a load capacitance connected at the output terminal, and we know that from where does this load capacitance values are coming. We know this thing. Okay, and the body of the PMOS is connected to power supply, and the body of the NMOS is connected to the ground. This is by default assumed. Okay, unless and otherwise it is stated something else. So this is the, we know that this is the drain, okay, and hence there would be a current flow if the PMOS is on and NMOS is on. There would be a current flow between between source and drain of PMOS, and we call this as the drain current flowing through PMOS, IDP. So it is flowing in this branch. Okay, similarly we will have a current flow when NMOS is on, and when NMOS is on we will have a current flow, and when the current is flowing in this branch, we call this as IDN, that is the drain current flowing across this NMOS. Okay, and this is a junction, this is a node. Okay, this is a node that is present between this branch, and this output branch. Okay, this output branch, and let us call this current as IC. IC. Okay, the current that's flowing through this output load capacitance, let's call this as IC. Okay, so when we apply KCL here at this node, we can easily we can write that IDP, the sum of incoming current, is equal to the sum of all outgoing currents, right? So this IDP is equal to IDN plus IC, or we can simply write that IC is equal to IDP minus IDN. Okay, so basically this equation will be coming, this is IDP, this is IDN. Okay, so this is a straightforward equation that's coming from this from the application of KCL at this node and this node. Okay, and we will use this equation many a times, so keep in mind this thing here. Okay, and what the delay times calculated using C load may slightly overestimate the actual inverter's delay. Okay, this is the thing, because we have assumed the simplistic things, and Now we will see the delay time definitions that are associated with the signals when the input signals are provided and output signal are being taken out from the circuit. Okay, so look at here, we have I have shown here two graphs. One is the plot for the input voltage, and this is the plot for output voltage. Okay, so let's if this and this is an inverter circuit, so if I can draw here a simple very quickly. Oh, this is the PMOS, this is PMOS. Okay, this is VDD, this is output terminal, and this is input terminal. Okay, this is PMOS, this is NMOS. Okay, and since this is an inverter, okay, and there would be a load capacitance present here, CL, between the output and the ground. Okay, see, this is CL or CLOAD, whatever. So first let us look at the input signal. So we had assumed that at the input side we are providing a pulse signal. Okay, the pulse signal, let us say that it is an ideal pulse signal. So this part, okay, this part that's coming here, and which is again going perpendicularly straight forward, then coming here, then coming down. Okay, this is basically representing the ideal pulse. Okay, ideal means this is ideal in the sense that it is not having any slope, it is going directly at 90 degree. Okay, when it is going, it is switching between 0 and 1 instantly, it's not taking any time to switch between 0 and 1. Okay, so if it is switching instantly without taking any delay, we call this an ideal signal. Okay, so when this ideal signal is applied, so for this part means from here to here it will be 0, and from here to here it will be a 1 high, and from here to here it will be a 0. Okay, so when it is 0, the output will be high, the output is 1 here, output is high. When it is 1, input is signal is 1, the output should be 0. So we can plot the output. Ideally, I am plotting this ideally. Okay, ideally this should be 0, and it changes to 0 here. So actually this is VOL mark. So this will, okay, start from here, and it will, ideally it should be like this. Okay, ideally it should be like this. This will become 1. Okay, for that assuming for the ideal case. Okay, but the things are not occurring in the ideal sense, because we are dealing with the practical signals, the real world signals. So let me delete these things for the ideal case, and I will draw the things for the real world cases, for more practical sense, for more practical cases. Okay, so this signal is a more practical signal. Look at this signal I am drawing here. I'm not drawing, this is already drawn, I'm just indicating that this signal that's coming here, and which is rising from VOL to VOH. Okay, look at this, this is VOL, this is VOH. Okay, so this is rising between the low and the high level. Okay, with a slope. So there is a slope. Okay, the slope is there. Okay, there is a definite, there is a limited slope here, there is a definite slope here. Okay, and then it remains, it after reaching VOS, it remains for a certain duration of time depending on its frequency, and then it starts to fall to 0 here, to 0 here, like this, and again it is having some sort of slope. So it rises with a slope and it falls with a slope. Okay, and after reaching VOL, it will stay here for a certain duration of time depending on its frequency, right? So let's if this is, let's say if this is the t naught time, and then t naught, and this is which one, t2. This is t2. Okay, so we have this level, VOL level and VOH level. VOL is the minimum level, VOH is the highest level, right? And we can define a V50% level, that is the mid point between VOL and VOH. Okay, so this 50% is the middle way, is the 50% is the mid value between VOL and VOH. Okay, and this is the level that is representing here, and which is represented by this line, okay. And the point at which it cuts, it intersects with this the voltage waveform. Let's call this at t naught time instant, and when it falls, let's call this as t2 time instant. Okay, this is for the input signal, the signal that's being provided at the input side. Okay, now we know that the output should be plotted, and which should be the inverted version of the input signal, right? Now actually what happens, so we had seen earlier the ideal case, the ideal fall and rise of the output signal, but practically how does it takes place is that, okay, here before t naught, we'll assume that the signal is 0. Okay, and between t naught and t2 the signal is assumed to be high. Okay, because below 50% level it's 0, let's say, and above 50% level it's 1, it's a high. Okay, now so at this intersect till this point, till this t naught, this is 0, input is 0, so output will be high, output is high, plotted here till t naught, output is high. Okay, here now from this t naught to t2, the input signal is 1 here, so the output should be 0 here. But how does it happen practically is that since this is coming from previous case, so we had not seen the complete picture here. Okay, we had just now we'll show the complete picture here. So when the signal becomes 1 here, okay, the output should drop to 0, and it drops to 0 actually, but it does not drop instantly, since this is a practical case and there are capacitances. Remember, this is the load capacitance here. Okay, load capacitance. So how does this output value is changing is that the output value is changing with respect to the charging and discharging of the load capacitance. Okay, when the load capacitance is charged, the output value is 1. When the load capacitance discharges, the output value is drops to 0. So this is how it acts. This is how the circuit, the inverter works. Okay, and this curve shows the discharging of the load capacitance. This curve shows the discharging of load capacitance. Okay, and you already know that in what sense the discharging of load capacitance occurs. It will follow this kind of curve. It will take some time to discharge, and we know that the discharging and discharging of load capacitance, there is a term known as time constant associated with those charging and discharging times, and we will see that thing. Okay, now when it starts to discharge, we know that at below 50% level, it is assumed that the signal level, output level is 0. Okay, it drops to 0, and above 50% it is high, 1. Okay, so here it is 1, here it is 1. Okay, when it just crosses this 50% line, okay, it drops to 0, it comes to 0, and we see that the transition has occurred. Okay, and so this time duration from here t0 to t1, where t1 is the intersection at the 50% mark, okay, for this curve. Okay, this is called as tau phl, the time the propagation delay when output falls from high to low. Tau p, the propagation delay when output falls from H to L, that is high to low. So tau p HL is the propagation delay when output falls from, or output goes from high to low. Okay, so this time duration between T0 and T1 is actually tau p HL. Okay, now it will come here, it will fall to VOL after certain duration of time. It will remain here because this is the lowest level, this is the lowest level, VOL. Okay, it cannot go beyond this, below this. And when the input changes from 1 to 0, the output should change from 0 to 1. Okay, so what happens that in this case the load capacitance starts to charge. The load capacitance starts to charge, and when it charges completely, we say that the output has become 1. Okay, so this charging of capacitance is shown by this curve. This curve represents the charging of the capacitance. Okay, and the instant at which it starts is T0, T2, and the time at which it crosses the 50% mark is T3. Okay, and this time duration is known as tau PLH, that is propagation delay for output to rise from low to high, L for low and H for high. So this is propagation delay time from low to high, and this is this T2 minus T3 minus T2 duration. Okay, and after certain duration of time it will reach to the maximum value VOH, and it will remain here for some time. Okay, so these are the delay time definitions associated with the input and output signals. Okay, and this is the 50% mark. What it is actually VOL plus half of VOH minus VOL, that is VOL this level, okay, this level, plus half of this portion, that is this portion. So this plus this becomes V 50% mark, and simplify this, it will become half of VOH plus VOL, that is this is actually half of VOH plus VOL. So VOH plus VOL divided by 2 gives you 50% mark. Simple, straightforward. Okay, and we had just seen this is tau PHL, that is this one, and tau PLH. Why is this called as tau PLH and tau PHL? Okay, and we can define average propagation delay parameter. Okay, which is nothing but the average of tau PHL and tau PLH, that is tau PHL plus tau PLH by 2. Okay, tau PLH plus tau PHL by 2. So these are the propagation delay time definitions associated with the waveform. Okay, and sometimes you will also find these rise and fall time definitions also. There would be somewhere you will see V 10%, in some situations you will see V 20%, but let's take here this 10% mark. So it clearly indicates that this is the 10% of the total, this is the 90% of the total. Okay, so it is basically 10% means VOL plus 10% of this VOH minus VOL. So if I can show in the diagram, so this is the V 10% mark, this is the V 10% mark. Okay, this is the complete, if this is the complete voltage, so 10% of this complete is this mark, and 90% of this complete is this mark. So this is 90%. Okay, so here it is assumed that okay, this is the VOL value. So VOL is not 0 here. VOL, this is VOL, and this is VOH. Okay, so this is the definition for V 10%. This is the by definition V 90%. Okay, and we can define a fall time and rise time accordingly. The fall time is TB minus TA, that is the fall time is this TB minus TA. Okay, means the time taken by the signal to fall from 90% mark to 10% mark. Okay, the fall time, and similarly the time taken by the signal to rise from 10% mark to the 90% mark is called as the rise time and fall time. So these are some more definitions again associated with the delay time analysis, the delay analysis of the circuits. So it will become it keep in mind, keep these definitions in your mind. This will be useful. Okay, and how did we start? So we started with all the capacitances that's being shown in the diagram. Then for simplification, we took all the capacitances, add up, and represented it by a single capacitance known as C load. Okay, and then the delay definitions that came into picture with reference to input and output signals. Okay, basically output signal, because tau PHL is defined when the output falls from high to low, and tau PLH is basically when the output falls from low to high, rise from low to high, right? Okay, and these are also associated with the output signals V 10% and V 90%. So the fall time for the output signal and the rise time for the output signal. But basically you can define these 4 parameters, that is tau PHL, tau PLH, and rise time and fall time for any given signal. Okay, the thing is that here we are more interested in the output signal, that how does the output signal is changing with respect to the input signal, and that's why we are defining these things for the output signal basically. Okay, so the next we will see the calculation of these delay time, that is tau PHL and tau PLH. Okay.